In this video, I'll talk about real gases. First, let's review ideal gases. The ideal gas law, PV equals nRT, is based on two assumptions. First, the size of the gas particles is negligible compared with the volume of the container of the gas. Second, there is no attraction between gas molecules. Let's talk about these two assumptions. First, let's imagine 1 mole water vapor in the gas phase with 1 bar pressure or 1 atm pressure at the room temperature. Its volume is roughly 24 liters. But what's the size of 1 mole water molecules, or 6 times 10 to the power of 23 water molecules? It's simple. Let's compact this huge number of water molecules as much as possible, and the volume is simply the volume of water liquid or water solid, approximately. That's roughly 20 milliliters. Therefore, the size of 1 mole water molecules is roughly 20 milliliters. The volume of the container of 1 mole water vapor, however, is 25 liters. 25 liters is roughly 1,000 times 20 milliliters. And therefore, we say the size of the gas particles is negligible compared with the volume of the gas container. How about the attraction between water molecules? Yes, it's significant in water liquid or ice. However, in the gas phase, water molecules are far from each other. The attraction between two water molecules decreases when the distance between the two molecules increases. Therefore, the attraction between water molecules in the gas phase is negligible. And then, even for water, we can say PV equals nRT for the gas phase of water vapor. What about real gases? We start from the ideal gas law, PV equals nRT, and we get pressure equals nRT over V. Based on two assumptions. One, the size of the gas particles is negligible. Two, there's no attraction. But what if the water molecules in the gas phase are really close to each other, and the molar volume of the water vapor is pretty small? And then we cannot simply neglect the size of the water molecules. We need to make a correction here. We need to subtract this MB from the volume of the container. Let me explain this MB. N is the number of moles of the water molecules. B is the size of 1 mole water molecules. B is roughly 20 milliliters per mole. Again, this is because 1 mole ice has a volume of roughly 20 milliliters. So when we include this correction, you will see when B increases, when you have a larger molecule, this V minus MB is smaller, and nRT over V minus MB is bigger. Therefore, if you have larger molecules or larger atoms, their real pressure is higher than nRT over V. Now let's look at this equation again for real gases. There's one more correction that includes parameter A. A stands for attraction. And it's a negative term. It's negative AN squared over V squared. Therefore, when attraction increases, pressure drops. How do we understand this? Again, just imagine a lot of gas particles keep colliding with the surface of the container, but then if those particles attract each other, that will reduce the number of collisions between the particles and the surface area because the particles are attracted toward the center of the container. Therefore, when you have a large attraction between gas particles, you will have lower pressure. And this equation is called Van der Waals equation, proposed by Van der Waals. It can be used to describe the behavior of real gases. And also, we can divide the top and bottom here by N. We get RT over molar volume minus B. We can also divide the top and bottom by N squared here, and then it becomes A over Vm squared. This expression is actually better because we no longer have the number of moles in this expression. Temperature, molar volume are both intensive properties. They do not depend on the amount of the gas. A and B are parameters, and we can simply use this equation to predict the pressure of real gases. One more thing, at a very high temperature and a very low pressure, the molar volume of the gas is very large. Why? Because we can still use this equation to estimate the molar volume. V over N is RT over P. When temperature is very high, pressure is low, RT over P is huge. Therefore, the molar volume is huge. And then the molar volume is much greater than B, the size of 1 mole molecules. And also, when molar volume is huge, A over Vm squared is negligible compared to this RT over V sub m minus B term. So we can write out these two approximations here. Again, when temperature is high, pressure is low, V sub m is huge, and then we say V sub m minus B is roughly V sub m. Another numerical example is this. 1 million minus 1 is roughly 1 million. Therefore, this pressure for the real gas can be approximated by just RT over Vm, and then minus A over Vm squared. So it's right here. Again, I simply assumed this MB is much smaller than V, or B is much smaller than molar volume. Now let's compare these two items. When V sub m is huge, this RT over V sub m is small. This A over V sub m squared is even smaller. You have a huge number squared on the bottom here. Therefore, between these two terms, we can neglect the second term. And then we get pressure equals RT over molar volume. And that's simply nRT over V. We get back to the ideal gas law. When the temperature is high, pressure is low, molar volume is huge. Again, the physical meaning of this is when temperature is high, pressure is low, we have a large volume per mole gas. Gas particles are far from each other. There's little to no attraction between the gas molecules. Also, the size of those molecules compared to the volume of the entire container is negligible as well. Now let's work on one example problem. Water has a larger attraction term and a smaller B term than CO2. Why? Water is simply a smaller molecule in size than CO2. Therefore, water has a smaller B. How about A, attraction? Well, water is a polar molecule between two polar molecules. The attraction is greater than that between two nonpolar molecules like CO2. So now let's compare the pressures of water and CO2, assuming they have the same molar volume and same temperature. We have to look at this equation again. the pressure of a real gas is equal to RT over Vm minus B. Subtract the attraction term A over molar volumes. For water, you have a larger A. That means you have lower pressure. For water, you have a smaller B. Also, it results in smaller pressure. Therefore, if everything else is the same, because water has a larger parameter A and a smaller parameter B than CO2, we know the pressure of water is smaller than the pressure of CO2. Now I'll let you work on one practice problem. Let's compare the pressure of water and the pressure of CH4. Again, they have the same molar volume and same temperature. I did not provide an answer here, but you can still easily compare the size of these two. You can tell the B of water is smaller than the B of CH4 because of the number of hydrogen atoms here is greater than this number of hydrogen atoms here. C and O has roughly the same atomic radius. So that's 1. 2, the attraction between two water molecules is much greater than the attraction between two methane molecules. So again, if you look at this equation to calculate the real pressure of water versus CO2, this A term for water is much greater, and there's a minus sign here. So I'll let you think about this and compare the pressures of water and CO2. And CH4.